I'm going to walk through with you guys the water and electrolyte section. This is domain 1, normal nutrition. If you're in Engman, it's on page 11. So we have, with water, we've basically got two categories. There's technically three, but insensible and sensible losses. And our insensible losses is going to be basically things like water losses you can't see. So this is going to be water that is lost through the breath and water that is lost through your skin. Now, this is not sweat. You can see sweat, right? But this is just moisture that comes through your skin and then evaporates in the air. So water loss that you're unaware of is insensible. And of insensible losses, we typically lose about a liter, 0.8 to 1.0 liters a day through basically our skin and our breath. So if you're thinking about, you're in the car and it's really cold outside, and your windows start getting really foggy and moisture is accumulating on them because there's, as my husband would say, mouth breathers in there. That is an insensible loss through your breath. Then sensible loss is going to be basically losses that you can see is kind of how I'm remembering it. And that is like through sweat, through urine, and even through feces. So in your intestines, right, you're going to be losing some water both through urine and feces. Now, when we're talking about water and electrolytes, I like to think about also something I remember learning in science class, the sodium-potassium pump. That's going to be really important to kind of understand in this section what's going on as far as electrolytes going in and out of cells. And, the sodium-potassium pump, too, is really important for our heart, which is also a pump, right? So when we're thinking about potassium, and if we get too much potassium, that actually can cause cardiac irregular cardiac rhythm, how about that? Or even heart failure. So kind of keep that in mind as we go through. But our electrolytes, typically we're going to be talking about intracellular versus extracellular. And our intracellular electrolytes are going to be potassium, that's our main one inside the cell, magnesium, and phosphorus. So intracellular, within the cells, magnesium, remember that it's a cofactor or a carrier, right? It's involved in over 300 reactions in the body. The main one I think of is the ADP to ATP uses magnesium. But anyway, but it's an activating enzyme. Our phosphorus, we know phosphorus, it will give or use a phosphate. And then, of course, our potassium, that's going to be our main intracellular electrolyte, and that's with water electrolyte balance, sodium-potassium pump, right? Now, extracellularly, or in our plasma, lymph, interstitial fluids, is going to be, our main one is going to be sodium. So sodium for our sodium-potassium pump, right? And then we also have calcium. Calcium, as we know, is involved with like the transmission of nerve impulses, muscle contraction. We have chloride, which is, I'd say probably another major one, which is dealing with water and electrolyte balance. They all are, but that's kind of just pointing out some different things about each of them. And then actually we have sodium chloride, sodium and chloride combined. And then we have our bicarbonate, our HCO3, that's going to be dealing a lot of times with our acid-base balance. So those are our electrolytes. Of these electrolytes, I would say there are three that we need to remember their molecular or their atomic weight. Why do we want to know their atomic weight? Because we want to be able to calculate their concentration. So the atomic weight of sodium is 23. And how we would calculate the concentration, which is going to be in milliequivalents, is we're going to take the milligrams that we're looking for. Maybe we're given milligrams. So maybe we're given 1,000 milligrams, which is 1 gram. So we're going to take milligrams over the atomic weight. And then we're going to times it by the valence. And I'm not 100% sure on this, but it works out for these three, so that's how I'm going to remember it, is the valence. So we have cations and anions. It has like a little plus or a little minus on top of it. All of these sodium, potassium have 1, and then your calcium has 2. So you can just remember that if you're using calcium, you're going to multiply it by 2. Anyway, so sodium is 23. So if we have 1 gram of sodium, or 1,000 milligrams, we're going to be 1,000 divided by 23 times 1, that valence there. So then our sodium concentration is going to be 43.5. Now, if we want to do that for potassium or calcium, potassium is going to be the same thing. So 1,000, or 1 gram, or whatever grams you're given, divided by 39, and that's going to give us 25.6. Then our calcium, that's the only one that's a little bit different here. It is going to be an atomic weight of 40. So we're going to take, if we have 1 gram, 1,000 milligrams divided by 40, times it by the valence, which is 2. It's got 2 little pluses on it. So 1,000 divided by the atomic weight of 40 times 2 is going to give us 50. So that is in milliequivalents, MEG, and that's going to give us our concentration of each one of those if we had 1 gram. So you can, if you're given the concentration, you could figure out how many grams you have, right? So just kind of keep that in mind. But memorizing, sodium is 23, potassium is 39, calcium is 40. And calcium, you got to multiply it by 2. All right, moving on.